The universe is not described with only a single atom, but it is a collection of multiple atoms in which you call them as molecules, and these molecules form solids, as well as other matters that you could see in the universe. Hello everyone, this is Understanding Physics, and we want to talk about molecules as well as solids throughout this entire discussion. So if you want to, so, bleh. So make sure to like and subscribe, and also please check the notes in the description for the notes throughout this entire discussion. So we should just start straight away with the discussion of joining atoms together, in which you call them as molecular bonding. So there are multiple types of molecular bonding. So I will list them all. We have ionic, you would have covalent, you also have hydrogen bonding, van der Waals bonding, and lastly you have metallic bonding. So what I want to show you is that these two are strong types of bonding, this and this guy, as well as the metallic bonding. They are strong bonding interactions, while the hydrogen and the van der Waals, these are weak. So they don't interact that much with other atoms, but it still influences the way that we see matter throughout this entire universe. So let's talk about the idea of a ionic bonding. So let's say if you have sodium, which has 11 electrons, and you have chlorine, which has 17 electrons. Now, if you see from the periodic table, you would see that chlorine is very close to argon, while sodium is very close to neon. And this actually influences certain things. The way that you could see stability is that if it has a full outer orbital. And so this is one of the main reasons why sodium could release its electron much more easily, because it wants to have a much more stable system. So it could just chuck out an electron out. And for chlorine, it is better for it to have 18 electrons, which means that it's gonna suck in an electron just to make it much more stable. And so if you actually try to analyze the amount of energy, such as the ionization energy, which is about 5.1 electron volts for the sodium, and for the chlorine, you would need to use 3.8 electron volts for you to put in the electron. And what ends up happening is that you have sodium plus as well as chlorine minus, which requires you to spend about 1.3 electron volts total. But this is if its distance is very far. But if you bring them close enough, it would have something which is called as the electrostatic force, as you have already known. And so this interaction between the positive and the negative will attract each other. But it won't go fully intact, because if it goes very close, you end up combining the nucleus. So there has to be a force that is repelling it. And this is where the nuclear force comes in, or pretty much the electrostatic from the nucleus. So you couldn't have the sodium and the chlorine go very close, because there are some of these nucleus which is still positively charged. So they also repel the atoms out. And so if you plot the energy with respect to the distance, what you would have is something like this, in which this is your distance, and it would have something like this. So this is your 1.3 electron volts, and then energy is 0 when it is at its neutral state. And so in here, when the energy goes to 0, this is the stable compound. And so this energy here from 0 towards this point here of about 4.2 electron volts for sodium chloride is what we call as the dissociation energy. The dissociation energy, which is the energy that you need for you to separate it into into a neutral sodium and a neutral chloride. So this part here is the nuclear interaction, and in here, this is the electrostatic of the charged particles. And so this is what governs the ionic bonding. So something like salt sodium chloride or calcium chloride and much more are governed by the ionic interaction. And it is pretty strong. It's pretty strong. And also, because it's pretty strong, it pretty much binds your electron into each of the compounds, because as you can see, chlorine is much more stable compared that to sodium. So it couldn't really transfer the electrons between the chlorine. So normally sodium chlorine is a crystalline matter, which we'll later discuss much more further. But anyways, the electron is strongly bounded by an atom. And so this is what causes it to become insulators, electrical insulators. And most of the time, electrical insulators normally corresponds to a heat insulator as well, which is sometimes true, but it really depends on the crystalline structure, which we'll later discuss later on when we discuss about the interaction between the vibration of the crystalline as well as the vibration of the electron wave. The second of all is the covalent bonding. So covalent bonding, if you know, this is the backbone of chemistry. Something like hydrogen, H2, you could have H2O, you have ammonia, which is like this, and so on. And so these things are governed by something which you call as covalent bonding. So covalent bonding is the idea where electrons are shared between each other. So something that you could see is, for example, H2O. H2O has, so it has one electron here, and technically you would have 6 electrons here. But instead of grabbing the electron for it to fill in the orbit, instead you share it between it, and this is much more stable. And so this is one of the solutions of the Schrodinger's equation, but it is pretty hard for you to compute about this straight away. So this is a very simple model that chemists normally use, in which you just imagine them to be sharing it, something like this. And so because of this, the electrons are pretty much bounded by the molecule itself. And so these molecules are normally insulators, since they cannot really transfer the electrons out. So after this, I'll jump into metallic bonding. And this is one of the last primary interactions between atoms, which governs chemical reactivity. And so metallic bonding is a very extreme case of covalent bonding, in which, let's say if you have iron, instead of it being bounded between the atoms here, instead the electron could freely roam around. So it is not really bounded by the atoms, but instead it is moving freely across the matter. And so this idea is something which we call as the free electron gas. And this is why metals are normally conductors. They are very good conductors, especially in electricity, as well as the thermal conductivity. And so metallic bonding is very common when you discuss about materials, since most of the things that I normally study is about materials, and one of the major things that we learn is about metals. So there's lots of ways that you could actually get an interpretation of why metals are the things that they are, thanks to this free electron gas. But I won't fully discuss about it within this series. But so if you want more discussion about materials in general, you can just leave it in the comments for me to discuss in a much more fuller manner. So let's move on to the secondary interactions. So we'll just introduce hydrogen bonding first. And hydrogen bonding is very related to induced dipole bonding, which I don't discuss here, but it works a very similar manner. So H2O is something like this. But if you know about oxygen, oxygen has oxygen has 6 protons, while the rest only has 1 proton. And this actually results in a much more stronger interaction towards the oxygen instead of the hydrogen, which actually forms a positive side as well as a negative side here because of the buildup of electrons. And this actually gives you like a polar dipole. And so if you have other H2Os, it will try to interact with the dipoles so that it will minimize the potential energy. And this is why, let's say, water to be so this is why water is liquid at room temperature and also freeze at 0 degrees Celsius. It is mostly because of the hydrogen bonding. So it's a pretty strong type of bonding, but not that strong, where to the point where you need lots of energy for you to break it. This is only using thermal energy, and you could still break it, which it turns out that it forms into gas. The last thing to talk about is the van der Waals bonding. And the van der Waals bonding is very similar to the hydrogen bonding, but instead of the interaction between the hydrogen and the oxygen, instead what we talk about is that let's say carbon monoxide, CO2. And so the electrons is propagating around the molecule, right? And so this means that from quantum mechanics, you'd know that there's a probability that the electron is found at a certain position. But this also means that other carbon monoxides could feel this tendency of a positive and a negative, and vice versa, which will later induce the electron to move closer to the positive side. And this will later form a chain reaction, and in the end, what you would have is something which you call as the van der Waals force, which is a very weak force. But if you do this at very low temperatures, it is very evident. One thing is that you could see like liquid nitrogen, liquid carbon dioxide at very low temperatures. And this is because of this interaction in which it is much more clumped together. So we have mostly talked about the bondings within chemistry, but let's try to dive into the physics a little bit. And let's talk about the energy levels. The energy level of molecules. So we should just base this idea from quantum mechanics. If you remember that there is quantization of angular momentum, which is L plus 1, h bar. And with only this, we could actually form what is the energy. So the energy of a spinning system is going to be I omega squared over 2. And L is I omega, right? And so this means that you could actually simplify this into L squared over 2I. And so this would later mean that this would be h bar squared L plus 1 over 2I. And this is the quantization of energy. So let's think about this further. The angular momentum here actually corresponds to, let's say, for example, HCl. And then, obviously, these guys doesn't really stay put. Instead, you could have it to have a certain energy just by having the hydrogen spinning around. And this quantization of energy comes from this guy here. So what we see here is that there is some form of a energy splitting. So this is from 0, 1, 2, and etc. Not only when we talk about rotational motion, but molecules could also vibrate. And so if you know about, let's say, HCl again, it will have this type of relation again. And if you go very close, if you go very close into this region, you could just approximate it to be a parabola, which is very similar to how you represent things with Taylor series with the second order term. It is this type of relation. And this type of relation, which we have already discussed when we did quantum mechanics, was the quantization of energy was n plus half h bar omega. And normally the omega here is about 10 to the power 14 per second. So this has the range of about IR, the infrared range. And this guy has the range of in the microwave. So this one has smaller wavelength. Compare that to this one. This one has a higher wavelength. So this means that this one uses low energy. This one has higher energy. And this one has lower energy. Oh, sorry, microwaves are way larger compared to this one. Sorry, my bad. So what we see is that if you look at a certain spectra, you should see the microwave interaction first. After that, you would see the vibrations. And so we could see this type of relation. So let's actually do a very thoughtful thinking. And let's think about, let's say, a jump. So the transition between, so let's say HCl, and let's say HCl is, we are observing the molecular spectra, which means that we are interested in the change in the energy. So obviously, which we have already discussed about the atomic spectra, is that they have selection rules. And so this is the same thing if we discuss about molecular spectra, in which it also has a selection rule, in which delta L must be plus or minus 1, and delta N must also be plus or minus 1. So we could do certain theories about this. So let's just think about changes of energy from, let's say, so if we just do a transition from n plus 1 to n, same thing, but that instead you would increase the change of L would, so instead you would think of L to be, so the L would change towards L plus 1, or you could have L plus 1 change to L. And let's see where this goes. If we think of the transition from n plus 1 to n, of L going to L plus 1, what do we see? If we observe the change of energy, so the total energy is n plus half h bar omega plus h bar squared over 2i L and L plus 1, right? And so the change of energy for the first condition is going to be just half h bar omega. So yeah, we will just do it like that. No. Actually it's fine. So we'll just leave it like that. And then instead we'll increase the energy in terms of the rotational motion. So this will be added with h bar squared over 2i. So it starts from L and goes towards L plus 1. It means that, well, you know what? We'll just do it from L minus 1 towards L. It's a much more simpler conversion. Oh, sorry. This should be negative then, because we are thinking about the change of energy. So this is negative. So it's that minus that, and then the L minus the L minus 1. So it's going to be, starting from L, it's the L times L plus 1 minus, substituting L minus 1, it's going to be L times L minus 1. And what we observe here is this is going to be negative h bar omega. If this is, so, okay, so the L's could be substituted outwards over I. And then what you would have left inside would be L plus 1 and L minus 1. So it's going to be, the 2 will cross out, the L would cross out, and this would be positive. So this is what we observe. So what we see is that it starts from negative, sorry, this should technically be, okay. So because we'll just assume h bar omega to be very large, so we'll just observe the change, sorry, just the modulus. So it will be h bar omega minus h bar squared over IL. So technically we are doing it in reverse. I'm so sorry about this. So anyways, this is if we increase L. But what if we decrease L? If we decrease L, the change of E is going to be, so we'll just do a negative straight away. So we start from n plus 1 and then subtract that by n, okay? I'm so sorry about the change of the notation. So it's going to be h bar omega plus, you know what? We could just do L towards L minus 1. That's a much more easier conversion. So it's plus, it's going to be h bar squared over I L. But instead it's positive. You could just prove it straight away. It turns out that you would get this to be positive. And here's something that I want you to take away. Is that you would see that there is discretized value. So if we try to plot this, let's say this is your energy. So at this point, this is what we call as the h bar omega, okay? So first of all, what I want to state is that the L couldn't be 0 in here, because what we did was we use a notation which results into a negative L, which is not possible. So we'll just assume that L is not 0, which means that there should be peaks at here and here, but not at the center. And the peaks are equally spaced of about h bar squared over I. Same thing in this direction. So what you would have is discretized peaks both in one direction as well as the other. And this corresponds to the region, so we'll just assume this is energy going up, which means that the one which has the higher energy, which is this direction, would be the when L goes downwards, or if you let your angular momentum drop, but if you go towards the left hand side in which the energy goes downwards, you're increasing the angular momentum. And so what you would see is that you could see the spectras in which you would know what's the moment of inertia of a particular object, of a particular molecule. It's a very powerful tool when you're trying to determine what's the molecule. You could just see its molecular spectra and observe this type of spectra. And so these spectra here corresponds to absorption of energy, and one of the crucial roles of this is UV protection. So something like the ozone. So the ozone actually keeps us safe from strong radiations of UV, but also there are also other gases in the air which also absorb certain energy for certain wavelengths, and that's why the sky is colored blue, because the molecules don't really absorb those blue color. So all of them are transmitted, and instead it falls into our eyes to observe that the sky is blue. And this is also true when you're looking at sunsets, looking at some other phenomena in which you would see the sky to be purple. It all depends on the angle and also how much of the transmitted light is being absorbed by chance or by probability. So now let's talk about solids. And so solids is one of the most crucial things that I study, which is talking about materials. And so one characteristic of materials is that you could actually separate these things into two: crystalline or amorphous. So obviously you would know what a crystal is, something like diamonds and others. And so what crystalline exactly mean is that it is a repeating pattern. So something like, so you could have a crystalline structure like this, it works. You could also make it in terms of a hexagon, and it repeats. We call this as crystalline. But amorphous is a much more random structure. So you could have it something like this. We call this as amorphous. And so obviously certain materials could be formed into crystallines or maybe amorphous depending on the process. But this is not a materials science course. So the process of you creating these kinds of stuff won't be discussed here. But I want to describe a lot about crystals. And this is because in crystals you have something which you call as the unit cell. And this unit cell is the thing that is repeating. And one of the things that we see of a crystalline material is that, one of the greatest example is sodium chloride. Sodium chloride is a salt, which is a very crystalline salt, in which its structure is something like this. It's like a checkerboard pattern of sodium as well as chloride. So it forms something like this. I'll just draw it like this. It's not to scale, but you would get the point. Like so. So it's a cubic structure, and it pretty much has like a octagonal interaction between the sodium as well as the chloride. And you could determine the energy. And let's actually think about the energy of this type of structure. So let's think about the energy straight away. The energy is just the sum of Ke squared over R, right? But it's depending on your I, and then the E squared is technically EI. And why EI? So EI actually corresponds to the charge of the sodium or the chloride. It depends on what you are interested in. And technically same thing for the other one, but in here we'll just assume that this is a sodium. So it's positive. And so if we try to sum this up for each of the atoms, what we'll see is something like this. We first see a sodium surrounded by, so the sodium is surrounded by chlorines. And there are 6 of these, so it's like a cubic structure. So it's 6 times the Ke squared over R, which is the distance from the chlorine towards the sodium, but it's negative because it's differently charged. So the first term is something like this. After that, there's another value in which it has interaction with the other sodium, and the distance could be computed from Pythagoras. So the distance is square root 2 of R, and then the Ke squared, but then how many of those are there? It turns out that there's 12 edges. So you could just compute it by yourself, but I will do it in here. So there's 12 of them. And then you do the same thing. It turns out that there's 8 corners, and the distance is about square root 3 of R and Ke squared. And you could do it so forth for the other sets of atoms. And so what we could see from here is that we could actually just extract off the negative Ke squared over R and collect 6 minus 12 over square root 2 plus 8 over square root 3 and so on. And this is what we call as the Madelung constant alpha. So depending on the crystal structure, it would have a different Madelung constant. But remember about this. This thing only considers electrostatic forces. So what we also need to consider is the repulsion as well. The repulsion from the atoms, in which we'll just express it as a over x to the power n, a to the power r to the power n. Now the equilibrium between the repulsion and the interaction of the electrostatic you could just sum them up into this total energy to be negative Ke squared alpha over R plus AR to the power n. Now, you would know that for a certain crystal, it must have a certain radius, right? And this radius must minimize the total internal energy. So we could just take the derivative with respect to R to figure out what is the minimum distance. So if we do this, it's alpha Ke squared over R squared plus, this is minus then, A over Rn plus 1 of n. and this must equal to 0. And so you could solve this. It turns out that your A is R0 n minus 1 alpha ke squared over n. So A and n are pretty much constants, but it turns out that the A is related to n, as well as you know what is the R0. And so what you could do is that you could just substitute this n back into your equation and factorize everything. What you would get is negative alpha ke squared over R0, which is the equilibrium distance, R0 over R minus 1 over n, R0 over R to the power of n, and close it all. And so if you plug in R0 into the mix, so this is the U, this is what we call as the ionic cohesive energy. And so this is how cohesive your material is, especially when you're talking about crystal materials. But in here, it's much more specifically for ionic interactions. So when we discuss about materials, we first only think about classical ideas. But now what I want to do is to bring up a quantum idea, which is something which you call as the band theory. So here's the idea. If you have two atoms together, let's say it has 1s and 2s, each of them are the same. Let's say it's hydrogen and hydrogen. You bring them together, and if you plotted it into a graph, what you would have is some splitting. Something like this. And so this type of splitting, if you do chemistry, you would have the 1 sigma and the 1 sigma star and so on. But if you do it for multiple hydrogens, what you would have is that you could just fill up this entire thing with lines, which ends up filling up this entire space in between. And for a specific, let's say R0 or the equilibrium distance, what you would have is it's like a filled state here. It's like a set of lines that you could fill. Like this. And this is what we call as bands. And the gap in between is something which you call as a band gap. So how do you determine something to be a conductor, insulator, or something else? So you could think of it as the filled states or the filled bands, as well as the empty bands. So for a conductor, the filled band is intersecting, or it is pretty much within the same band as the unoccupied. So this is unoccupied, this is occupied. So you could apply a very small energy for it to jump into a higher state in which it is pretty much free. So it could roam around. This is why you call this as conductors. But if you have a gap between the filled states and the unoccupied states, you would need additional energy for it to jump up. And for semiconductors, this band gap is smaller than the room temperature. So what you would have is that the electrons could jump frequently for it to act like a conductor. But you could also change the distance just to change the resistivity, how much that it is insulating, so that you would need to apply a much more higher voltage for it to jump up. It's also possible. But if the energy gap is much more larger, you call this as insulators, meaning that you would need a large amount of electric field for you to jump it up. And this normally counts as something called the dielectric breakdown anyways. Now, when we discuss about semiconductors, we also discuss about p-type and n-type. So the way that you could visualize p-type and n-type is the following. You would have the filled bands, but not only that you have filled bands. For n-type you introduce something which has more electrons, something like, let's say, phosphor. And this phosphor actually fills in the band right around there. And so this energy state is something which we call as the something which we call as the acceptor level. Sorry, this is the donor level, sorry, my bad. And then the top and the bottom is something which we call as the conduction band and the valence band. So for n-type, you would introduce more electrons so that you introduce a donor level of electrons, and these electrons could jump much more faster compared that to the one from the valence band going up. This is an n-type semiconductor. But what about if you introduce boron into your silicon? What you would have is that you would introduce more states at the bottom, which we call this as the acceptor level. And these guys are empty. So you could just apply small energy for it to jump, and so it is pretty much free at the state. And this is what separates a p-type and an n-type. So what I want to discuss right now is the idea of a metallic conductor. And metallic conductors are normally discussed in terms of a free electron within a particular solid. And normally you could just think of it as, let's say, like a small cube. Let's say it's a unit cube with length 1 each. And the electron is free to roam around. So if you remember from the idea of quantum mechanics, in which we have already developed, what we know is that the energy would be h bar squared over 8 ml squared n squared. And so the n here corresponds to the numbers. It's just pretty much the square root of nx and y and nz squared each. And so these numbers here pretty much corresponds to the allowed states. So what I'm very interested in is the amount of state within this 1 by 1 within the maximum value of, let's say, the maximum value of E, which corresponds to an n. So we go from 0 to n of the integral 4 pi over 8 n squared dn times 1, because within one section in which it has distance of dn between the sides, there's only one state total. It's technically 1/8 of a state, but there's 8 of them, which corresponds to 1. So you would have this integral, which means that you could conclude, oh wait, sorry, and then there's two electron spins for each of the states, meaning that you could get the integral to be pi over 3 n cubed from 0 to n, right? Which is this value. But if we consider the maximum value to be EF, or which we normally call as the Fermi energy, which must be equal to h bar squared over 8m of n squared, if you substitute that in, what you would get is pi over 3, 8m over h bar squared of the EF, take the square root and everything cubed. So simplifying this much more further, what you would get is pi over 3, 2 to the power of 9 over 2, m to the power 3 over 2, EF 3 to the power 3 over 2 over h bar squared. Sorry, h bar cubed. Now if you change the maximum energy, so the dn over dEF technically, or in which we'll just conclude this, something which we call as the g of E, it will be pi over 3 of 2 to the power 7 over 2 m3 over 2 over h bar cubed. Oh, sorry, there's no 3 anymore. Okay, and so this is what you should get. Oh, sorry, there should also be the square root of E here. So this is what you exactly get. And so the idea of EF actually corresponds to the maximum value, corresponds to the highest, EF corresponds to the highest field state, highest filled state. That's the thing. It's about the filled state. But G of E corresponds to the amount of states per energy. And so this actually corresponds to something like this curve here, in which this is the curve G of E, and then the amount of area within it is the amount of states that is available, the amount of states that is filled. No, sorry, if this is EF, this is the filled state. But this only works when temperature equals to 0 Kelvin. So the actual definition of a Fermi energy level is the highest filled state when it is 0 Kelvin, or the probability of finding electron at the given state, EF, to be about 50%. So if it is not within 0 Kelvin, the curve would still be the same. So the curve will be something like this, but the amount of energy, the amount of states goes something like this. And the place where it is half is something which you call as the Fermi energy. So there's lots of discussions of the Fermi energy level as well as the others when you talk about material science, especially when you talk about semiconductors, in which something that we will be discussing right now. So if you want more discussion about the Fermi energy level, you can just leave it in the comments below. But let's go ahead and talk about the semiconductor now, because we understand about bands now, in which it has filled states as well as empty states. So for a semiconductor, normally the Fermi energy level is at the middle. So this means that at the bottom it is mostly filled, and then at the top it's mostly empty. Well, this is at 0 Kelvin. If there's temperature, some of them will jump up, depending on the probability. So let's think of this. If, let's say, we add some N atoms, or technically what we call this is the N-type atoms, or phosphor, let's say, and then we put it into our silicon semiconductor, what you introduce is this new state, which we call as the donor level. So the top is something which we call as the conduction band, and the bottom is the valence band. So normally the valence band is filled and the conduction band is empty. And the donor level is filled with electrons at 0 Kelvin. And if you apply some heat or thermal energy, it would jump quite frequently. These electrons will jump quite frequently, thus resulting into a behavior of a conductor. But if you add in p-type atoms, or like boron, what you introduce is another energy level, which you call as the acceptor level. And this is where holes exist, meaning that the electrons could jump up. But remember, when we talked about electrons jumping up, you could also describe as holes jumping down. And this is very important because when we thought of antimatter, we describe it of something like a hole. And this is what we normally do in the semiconductor industry. Let's try to understand the p-n junctions in a much more better understanding. So last time we discussed about the p-n junction as something like this. So there are additional holes here for the electrons to fill in, such that there's a negative field here and a positive field here. And so from electrostatic, we know that there is an electric field going in this direction. So it goes from the positive towards the negative. And so this is what we call as the internal electric field. This is what I normally call it anyways. Internal electric field. Now, instead of looking at like this, we'll just look at it in terms of the p-n junction. So it will be something like this. Whoops. If we just do it like this, there we go. So this is the acceptor level. This is the valence level. So the bottom is the valence band. And at the top, this is the conduction level. And donor level. And at the top is the conduction band. Now remember when we talk about the p-n junction, in which if you have some heat, let's say, the electrons in the donor level would jump up, meaning that it would be building up positive here. There will be holes here. So this is the drop-off holes. And in here, so at the top, you would have a charge buildup of so there's the electrons at the top. And then at the bottom here, what you would have is a charge buildup that is dropping down all of your holes, bringing up the electrons, which makes this much more negative. And then the conduction band and the valence band allows for the electrons and the holes to escape, meaning that you would have a buildup of positive and negative, meaning that you would have an electric field, right? So this means that your electron would move towards this direction, and your holes move towards in this direction. So that's the first thought experiment, right? Now, what if we apply a electric field in this direction? What would happen is that, so if we just sketch this again, something like so, if we apply a bigger electric field in that direction, what would happen is like these protons would be dropped down and then trying to go in this direction in which it is blocked. And same thing for the electrons. The electrons which has already jumped up will try to move in this direction which is blocked. And so this is what we call as the reverse bias, in which it turns out that it becomes into a higher, it will increase its resistance. But if you do it in the other direction, so if we do it like this, but instead we apply an electric field within this direction, what ends up happening is that your holes will try to move in this direction, which is still available, and the other holes will try to move in this direction, thus having much more slots for it to fill because it is emptying out. Same thing for the electrons. The electrons is moving in this direction, and the electrons are going in and dropping down, reducing the resistance. And this is how a diode works. You cancel out one direction for it to favor another direction. Another thing that you could now think of because of this energy diagram is that you could think of a photovoltaic cell or a solar cell. So let's say a solar panel. So if you have holes already dropping down, what you could do is that you could have light shine at an electron for it to jump up and move. And you could do so for all of these electrons here, thus creating energy. And then because of this energy filling up, it would also try to drop down into these holes. It would also try to drop down into these holes, which will actually produce energy as well. And so the usable energy would be about this guy here, the gap between the donor level and the acceptor level. And this is the only usable energy. And so engineers try to maximize this usable energy by tweaking the materials for you to produce the maximum amount of energy without spending too much of the energy in other places. Lastly, I want to talk about superconductors. So remember last time in which we discussed about superconductors in which resistance is zero? Now we want to try to understand this in a much more deeper level. So there are two types of superconductors. You have type 1 and type 2. Type 1 has it to have its, so let's say if this is the applied magnetic field and this is the magnet and this is what it feels, it would be something like this. And then it will drop. So what does this mean? So what I'm trying to express here is that if you apply, this is the applied. So if you apply a magnetic field, the magnetization would increase. Technically it increased in the opposite direction of the H, and then it will later drop at a certain H, in which this is called as the critical field. And for type 2, it is very similar, but instead of straightaway dropping, it has this exponential dropping until going to 0, in which it has two critical fields. And these two things only work at a certain temperature below the transition temperature. And so transition temperatures are very low. And so what researchers are now doing is that they are trying to increase the transition temperature just by trying to find new materials. And so there's a very big question that is being asked. Why does it have magnetization? And so this is a very interesting theory. No, sorry. This is the explanation. If you have a magnetic field applied to an object, there are electrons moving all around. But because it feels a magnetic field, it will try to move. Sorry, there is an applied magnetic field which is sudden. So it wants to try to go in the opposite direction. It wants to counteract this changing magnetic field. And this results in current forming. Now, because of this current forming, and there is no resistance, in the end what you would have is a persistent current that is flowing through around the system, thus producing a magnetic field to be zero. This is the explanation of how superconductors work. But why does superconductors work? Why is there no resistance within your material? Isn't there atoms that it could scatter, thus producing heat? And the answer is yes, there is. But there's a very interesting interaction that causes electrons to feel as if it doesn't have any resistance. And this is the BCS theory. So the BCS theory, and this is developed by 3 different people, and one of them is Cooper. So Cooper developed the idea of Cooper pairs. So what does the Cooper pair tells you? So if you have your crystal lattice, and let's say you have an electron moving. An electron moving here not only has resistance thanks to the lattice, but it also deforms it a little bit. And this deformity produces an pull on another electron, which will propel it much more further forward. This is the way that I understand this, and so if the time difference is pretty small, or the perfect amount, what you would have is one of them slowing down and then the other speeding up. But you could do this for multiple pairs, so that almost all of them feels as if they are accelerated and decelerated as well. And this is how I literally understand superconductivity. And I know this is not a very concrete explanation of superconductivity, but there are papers about this that you could read as long as you understand some quantum physics as well. But I won't be discussing all of that within this video. And so that's all for today's video. And so on the next video, what we'll do is that we'll discuss about the nucleus itself, as well as the physics behind it. So thank you very much for watching. Make sure to like and subscribe, and also please share this to your friends who really needs to understand physics in a much more deeper understanding. This is Understanding Physics, and I will see you on the next video.